Okay, Assalamualaikum warahmatullahi wabarakatuh, and a very good day. So we continue on the forward converter, but more on the analysis of the inductor current. So actually, the inductor current that we are focusing is actually the IL magnetizing. Okay, the magnetizing inductance, which is the current is actually here. Okay, this is the ILM. Okay, so if you look at this slide, so this is actually the summary of all the currents and also voltage waveform for this forward converter. So this is the current that flow inside this ILX. Okay, so this is during on state, and then this is during off state. Okay, so we have magnetized, we have the during on, so it will charge, and during off it will discharge. Okay, so that is for the ILX. And the second graph here shows the graph for this current ILM. Okay, and the third graph here shows the I primary, which is this one, I1. So as you can see, the I here that cross the LX is equal to I primary. So we assume that in this analysis, all the ratio between N1 and N2 is equal to 1, and also N1, N3 is also equal to 1. So this transformer, it just provide an isolation. Okay, the function is actually for the isolation. So as you can see here, the I at the secondary part here, we follow the primary, while during the off state, as you can see, during the off state, the I1 is actually equal to I1 is actually equal to IL magnetizing inductance. So this is all T, okay, T, because during the off state where the switch is off, the current will flow from L1, LM like this, okay? So meaning that I1 is negative ILM. So that's why we have a negative ILM here. And this is the graph for I2. So this is the graph for I2 here. So as you can see, during on state, this diode will short circuit, will off-fault bias, so it will short circuit. So that's why we have the I2 here, which is equal to I1. And during this off state, as you can see here, the current is 0 because during the switch off condition, this one is reverse bias, so that's why I2 is equal to 0. And this is actually for the current that cross this third winding. So as you can see, during on state, there is no current because this diode will reverse bias, but during off state, we can see that actually the direction current is like this. So we have this diode forward bias, and so we have this current. So this current is actually equals to the current of ILM. Okay, and then this is actually the voltage across this LX. Okay, so we, but however, the forward converter got some limitation where it need to ensure that the ILM must equal to 0 before the next cycle. Okay, so if the ILM is not going back to 0, it will saturate the core of this transformer and may cause the transformer to malfunction. So actually, based on the graph here, to make sure that the ILM goes back to 0 before the next cycle, the theory said that it is depend on the duty cycle. Okay, it depends on the duty cycle. So meaning that it has what we call a maximum duty cycle, that there is a maximum value for this. So meaning that it has some limitation on the selection of the duty cycle. So in this slide also we will derive what is the value of the maximum duty cycle that is allowed for forward converter to be operated without malfunctioning the transformer. Okay, so let's look back at the change of delta IL. So right now, switch on, during the switch on, okay, during the switch on, when the switch is on, we can say that the voltage across the magnetizing inductance is equal to V1, and we can actually just shortcut, which is, I hope you all actually understand what it's all about. Okay, over Lm multiplied with dt, and since this is the switch is closed, so meaning that V1 is actually your VDC, right? So I can write down this is VDC over Lm dt. So this is actually my equation, okay, when switch is on. So cut this one, okay, here, and then I remove. Okay, right now let's continue when the switch is off. So when the switch off, so what is the VLM? So when the switch is off, the current will flow through the LM. So actually the energy will actually de-energize. Okay, so the KVL is actually VLM positive minus V1 is equal to 0. So from here we can say that VLM is equal to V1. Okay, VLM is equal to V1, and right now this diode is actually a forward bias. So it is, so meaning that V3 is actually equal to negative VDC. Okay, and then so we have this one VLM, so we can actually shortcut here. So actually this one will be delta ILM during off state over the duties over the time delta time of off, which is this one we call maybe change of Tx. Okay, this is actually T off, and this one should be equal to V1 over Lm. But I would like to state that this V1 is equal to V3 multiplied with N3 over N1, and V3 based on the circuit is actually equal to is equal to negative VDC, okay, based on this circuit. Okay, so I can say that my V1 is equal to negative VDC N3 over N1. So by substitute this into this, I can actually write down is equal to negative VDC N3 N1 over Lm. Okay, multiply with delta Tx. So this one will be my delta ILM off. Okay. Okay, so then I cut this one. Okay, so then I remove this all. And then in steady state, I mentioned before that the magnitude of delta IL on, which is the magnitude minus delta IL off, should be equal to 0, right? Okay. So by equating this, so this one is V dc dt over Lm is equal to V dc n3 n1 over dx over Lm. I can find out this one can be cancelled out, this one also can be cancelled out. So actually the Tx here, which is referring to the T off, is equal to N1 over N3 dt. Okay. Okay. And to make sure that ILM goes back to 0 before the next cycle, so mean that dt, which is the time during T on, plus the T off must actually must be actually less than the period. Okay, so we substitute dt and then delta t as a n1 over n3 dt, and the maximum time is actually equal to t. So I can write down this one is equal to d1 plus n1 over n3 is equal to 1. Okay, so and then okay, and then I can bring this one to here. And if we assume that n1 and of the ratio is 1, so I can write down this one is equal to 1 plus 1 equal to 1. So we have 2d is equal to 1, meaning that d max, that is the limit, the maximum duty cycle that is allowed for this Foward converter to operate without malfunction. The transformer can be 1 over 2 or 0.5. So meaning that d max is 0.5. So that's proof. Okay, this is actually the maximum duty cycle for the Foward. So meaning that if you want to operate your Foward converter, you cannot operate duty cycle larger than 0.5 because it will saturate the transformer. Okay. Okay, so next we go for the ripple voltage. So actually for the ripple voltage for this Foward converter has no different with the buck converter, because Foward converter is a buck converter with isolation. So just referring to our slides. Okay, just referring to our slide, the output voltage ripple is actually this one. Okay, just write down the delta V out is actually 1 minus D L LX CF or 2 V out. So this is voltage ripple. Okay, so D as a unit, and this one is actually ripple factor. Okay, so that's all. Conclusion of the Foward converter that include the analysis on the inductor current and also the output voltage ripple. So thank you very much. So we continue with the last isolated DC-DC converter, which is the full bridge and also the half bridge converter.